just this. Okay. Not x. It's omega. X of omega, it's lowercase x. This argument of the probability function is always a subset of the sample space. So, and also this capital X is a random variable. So it's a function. So function equal to a value doesn't make sense, right? But this is just a shorthand notation for this subset. Okay? So don't get confused. This is just a convention. Okay. So, and also for discrete random variables, this as a function of small x, this can be defined as, let's say, this is a function of, how should I write? Let's say p x of x. So this subscript is this capital letter, and this argument here is the value. Okay, so this can be regarded as a function of lowercase x. Okay, values of random variables. So as a function of the values, possible values of random variables, this is called probability function or probability mass function. So probability mass function. Okay, or sometimes we say probability distribution function, but the word distribution should be used for another concept in mathematical probability theory. Okay, so let's define cumulative distribution function then. So if we have the probability space, usual probability space, where we have a sample space, its sim algebra, and a probability measure. It's a probability space. Probability space. And x is a random variable. So that means x is a function from omega to real numbers, and also x is a measurable function. Then we define the cumulative distribution function. Cumulative distribution function. Or we just say distribution function. Okay. In statistics, we usually use cumulative distribution function or CDF. But in mathematics, in probability theory as a field of mathematics, we just say distribution function. So when we say just distribution function, it doesn't mean probability distribution function. It means cumulative distribution function. So anyway, so cumulative distribution function f of lowercase x is defined as the probability that the random variable takes the value less than or equal to this lowercase x. That's it. Okay, so now we are considering discrete random variables, so we can count each values of x, like x equal to 0, 1, 2, 3, up to whatever value. So in that case, this cumulative distribution function can be expressed as like summation. For example, in the case of rats, the possible values for this random variable, the litter size was 1 to 12 integers. So it's just the sum of all possible values up to lowercase x. So this is some constant. So if this x is 7, we stop at 7. If this x is 11, we stop at 11. Okay, and of course, in the case of rats, the maximum value was x equal to 12, right? So if we add up to 12, that means we are adding all possible values, and that should be equal to 1 because the total probability should be 1. Okay, so let's see. Maybe I should look at okay, so this is the frequency distribution, and where's the cumulative distribution? Oh no, we don't have it. Okay, so in general, cumulative distribution function is monotone non-decreasing function. Okay, what that means is if we plot this CDF, cumulative distribution function, well, depending on the random variable, this value can take negative values or positive values or whatever values. But whatever the distribution is, this cumulative distribution function does not decrease. It only increases, or it will stay constant. Okay, like this. And as we go to x infinity, it will converge to 1 at some point. And if we take the value of x to negative infinity, it will converge to 0. Because there should be some minimum values below which no value is possible. Okay, so it will be 0 and it will be 1. The exact shape of this function varies depending on the probability distribution. Sometimes it will look like 0 and straight line and 1. Sometimes it will increase like this. Sometimes it will increase like this. It depends. So example for coin tossing. Remember last week we studied coin tossing of two dice. Dice, throwing dice, two dice. Okay, coin tossing of dice doesn't make sense. Okay, two dice. Remember. So we have this probability. This is sum of the points of two dice. This can vary from 2 to 12. So these can be considered as the values of some random variable. Okay. In this unbiased case, let's consider this unbiased case. In this case, what we have as the sample space was the pairs of two numbers from 1 to 6. Alright, so this was the sample space. And the sigma algebra was the power set. Okay. And the probability measure, okay, of each pair was 1 over 36. Okay. So, so in this case, the random variable is a function from this omega to the set of these numbers, right? So it's actually like the defined like this. So this oh, random variable is defined for each pair of dice as k plus l. Okay. So we have omega, 36 points, and we have, I don't know, let's subset of real numbers actually. So from 2 to 12. Actually, we can take entire real number, but other values, other values other than these 11 numbers will have no corresponding points in omega. So the inverse images will be empty set. Okay, and the probability measure of the empty set is 0. So that happens with probability 0. Effectively, that means it almost surely doesn't happen. Okay, but these values are possible, 2 to 12. So it has some corresponding elements in omega, and for which we can calculate the probability by dividing the number of ways to obtain that by 36. Okay, then we can plot the probability mass function like this, and we can calculate the cumulative distribution function like this. So this graph plot is basically obtained by adding all these bars one by one. So the first for this point 2 is something like 0.002 something, right? So the corresponding value is 0.02 something. So this value is obtained by adding this value plus the next value, this value. Then the next value here is obtained by adding to this value the next value. This value. Okay, so then we can calculate the cumulative distribution function. So it will increase rapidly, then slowly in this case. Okay, that's because it has a peak here. Okay. Now let's move on to continuous random variables. Okay. So as we defined before, continuous random variable is a random variable that can take uncountable number of values. Okay, so here's a result of some experiment of measuring 338 silver pennies of the pointed helmet type of synod. I don't know what that means, but anyway, someone measured the weight of some silver pennies, coins. Okay, And here are the ranges intervals of weight. The weight is a continuous variable. So it can take any, usually positive values. It's not